the big functional programming conferences you always hear about. So it's really amazing to be able to be participating the first time and be speaking. So thank you for the opportunity, and thank you everyone who's taking the time to be here. So today I'm here to talk to you about ZIO Query. So ZIO Query is a library for writing optimized queries to data sources in Scala in a high-level compositional style. It's based on a paper, this one called There Is No Fork, by Simon Marlowe, as well as a couple of other folks at Facebook. And Simon in particular, he literally wrote the book on asynchronous and concurrent programming in Haskell, which is also a great book, even if you're doing asynchronous and concurrent programming in a language other than Haskell. So I definitely want to give a tremendous amount of credit to them. They did a library called Haxel in Haskell based on that same work. So if you're familiar with that, you're definitely going to be seeing some things that you're probably familiar with from there. But as we go through, I'm also going to highlight some of the significant differences there. So the problem that we're trying to solve here, you can really think about as this issue of balancing composability and performance. So here we've got a pretty simple application where we're going to get some user IDs, and then we've got a method that with each of our user IDs, we can get the username. So we've got this simple program here where I'm going to get all these user IDs, and then in parallel, for each user ID, I'm going to get the username, and I'm going to return the usernames here. So there are some things that are definitely good about this. This is very composable here. We've got this get all user IDs function that its only responsibility is getting those user IDs. And we don't need to know anything about how it's implemented other than that it's giving us back those user IDs. We've got this get username by ID function that, again, it's just taking care of one thing. It's just give me an ID, I'll give you back the username. It's taking care of that implementation. And then within ZIO, where you've got a for comprehension here. So this effect system is taking care of the idea of managing these sequential computations here. And we've got this for each par operator here that's taking care of doing all of these things in parallel, managing, creating fibers to do them, shutting down those fibers, taking care of all that for us. So we've got really nice composability and generality here. But the problem is this isn't going to be performant because we have essentially what we could call the n+1 selects problem here of we have all these different IDs we want to get. And for every one of them, we're separately hitting this database or whatever is underlying this that's containing these user IDs with a separate request. Whereas really what we want to say is we need all of these at once, and we'd want to send this as one request. So one thing we could think about doing here is we could say, okay, well, the problem is just we essentially need a new primitive here. So we could say that instead of having a function that just takes one user ID and returns one username, we could have a function that takes a whole list of user IDs and returns a whole list of usernames. And in this simple example, that would work, but we can pretty quickly see that that's not going to scale up for us. Okay, maybe we can say we're going to have kind of a collection variant of each of our getter methods for this data source, but what if we want to get the username and we want to get the user's friends or the user's date of birth or who knows what else? We can't have separate combinators for every combination of fields that we want to get from this data source. That's not going to scale to anything that has more than one or two fields. So how do we solve this problem? Well, so this is really where this Z query data type, that's the key data type underlying ZIO query, comes in. And so what Z query is going to let us do is we can redefine each of those methods in terms of a Z query instead of a ZIO effect. They're still going to return the exact same thing. So this is just going to take a single user ID and return the username associated with it. And we're going to be able to use that same type of compositional logic. And in fact, it's going to look very similar to what we wrote if we were using any other effect system. We've got a version of that same for each par operator. We get to use flat map and for comprehensions here. But this thing is automatically going to batch all of these queries for us here. So this whole thing is only going to get done in 2 requests to the data source, instead of, if we had, say, 20 user IDs we were getting, we'd be doing 20 requests to the data source here. So this is how we get back, we keep that composability and generality we had when we just did it with a simple effect system like ZIO, but we also get that performance without having to have all of these specialized variants for every combination of data that we want to get. And this is really important if we want to be able to support solutions that do more complex things with data sources. So part of how this project originated is working with Caliban, which we're going to get into more in a little while, but is a GraphQL library for Scala, where great solution there for building schemas in a type-safe way and for creating front ends and back ends there. But if we don't have something like this, we can end up doing more queries than we need to. So this lets us optimize those while retaining this type of straightforward style of writing what we're doing. So how does this actually work under the hood? So we're going to take a pretty traditional approach for functional programming of we're going to separate the description and the interpretation of a query. So instead of doing all these queries immediately, we're going to capture them in a data structure that reflects the parallel and sequential structure of some queries. We need to do one thing before we can do something else, right? Like in that previous example, we needed to get the user IDs before we could get the usernames for those. And some things we can do in parallel. Once we have a set of user IDs, we can get all the usernames at the same time. Then once we have that data structure, we can then think about interpreting that of, we're going to explore that entire data structure. We're going to find everything that can potentially be done in parallel before we have to take another sequential step. We're going to do all those things. Then we're going to re-explore that data structure, find everything else we can execute in parallel, and we're going to keep doing that until we've explored this entire data structure that describes this query, and we have all the results of the query. So let's see what that starts to look like in code here. So the key data type in ZIO Query is this Z query, which is really defined in terms of this one method here that essentially describes taking one step in evaluating this query. And so this is an effect that is going to allow us to have an arbitrary environment. So if you're familiar with ZIO and how the environment type is used as either a reader monad effect, or you can think of it as just allowing you to model the capabilities that your program requires, you can have the same type of environmental requirements for any query that you could for a ZIO effect. And it's also going to build in this query context, which essentially includes a cache and logging and other facilities that are going to help us do this query. It can't fail, but it's going to return this result. And a result can either be done with a value of A, it can be failed with an E, or it can be blocked on some set of requests to data sources with a continuation that we can execute after we get the result from those requests. So let's see what that looks like. So again, we have this done constructor, which is just going to give us a value. We have this fail constructor, which is going to fail with a cause, which if you're familiar with ZIO, this is just a data type that lets us describe potentially multiple errors if we have something that fails for more than one reason, because say we did two things in parallel and both of them failed. And then finally, we have this block constructor here that's going to have a set of requests to data sources that we need to execute. And once they're done, is going to have a continuation that's another Z query that will eventually return us that A. So with this, the first thing we can do is we can model sequential queries. So we can implement a flat map operator that just lets us say, I need to do this query, and then I need to do another query after that. And essentially here, we're going to take this step, and we're going to look at its result. If it's just done with a value of type A, then we can just call F to get a new query and take a step with that. If the first query failed, then we can short circuit. We don't even need to do the continuation. We'll just return that failure. And the interesting one here is this block constructor, where we say if we're already blocked on some set of requests that we need to make to a data source, well, we're still blocked on the same requests. And all we're going to do is we're going to add this new query to the continuation. This is just one more step that we need to do when we get back the results from the data source. So far we haven't optimized anything, but we've seen how we can use this to express sequential computations. So we've got a lot of flexibility here of when we need to do one thing and then do another thing, we can express that here. Where the optimization comes in, and apologies, this gets a little bit small here, is when we're doing parallel queries with this zip with par operator. And so if we've got two different queries that don't depend on each other and we can do in parallel, then we can look at both of them. And a lot of these situations are pretty straightforward, that if either of them fails, we'll just return the failure. If both of them fails, we'll put the failures together and return both of the failures. If both of them are done, we'll just combine the results. But the interesting cases are these first three here, and particularly the first one. So if one is done with a value and the other is blocked on some set of requests, then we're still blocked on the same set of requests to a data source. And once we get that back, we'll just take that value we already have and include it in the results. And same thing the other way around. But where the optimization really comes in is here, of if we've got two different queries that are both blocked on some set of requests to data sources and both have continuations, we can just combine those into one that's blocked on both sets of requests. And then once both sets of requests are completed, we can run both continuations and combine the results together. So this is where that parallelism comes in, that going back to our original example, when we had those, say, 20 different requests for the username with a user ID, instead of running those one at a time, when we call that zip with par or operators that are implemented in terms of it like that for each par, we're just going to combine this data structure together to get one larger query that's going to include all of the requests just as data here, and then it's going to return the continuation of them. So we talked here about requests and data sources. Let's see a little bit more about what some of these are. So a request is essentially just a marker trait. It's just a data type that describes what some request is going to return without itself describing the logic of how that's going to be executed. So a request is just something that is going to ultimately return a value of type A or failed with a value of type E. So we can imagine if we have a user request, it might succeed with the username and fail with a throwable or fail with nothing. And it's just going to be a data type that describes the inputs and the outputs of what we expect. It's not going to describe any logic of how that request is executed. A data source then is what's going to contain that logic of how we execute these. So a data source is something that potentially requires environment R and can accept requests of type A. And it's going to require implementing this run method that takes a set of requests. So not just one request, but a group of requests, and is going to return this completed request map, which you can think of as a kind of sink that allows you in a type-safe way to return the results of these requests. Because these requests might all be, say, user requests, but user request might be an algebraic data type that has some subtypes that return integers and subtypes that return strings and some subtypes that return users. And so we need to make sure that each time we put a value in here, the type that we're returning corresponds to the type of the request, but they're not all going to be the same types. So that's what the completed request map here does. And the really important thing here is that this run method is taking a collection of requests instead of a single request. So when we go to implement this data source, we're going to be able to introspect on all of those requests that are potentially being executed in parallel and do those in the optimal way. For example, only doing one request to an underlying database here instead of doing multiple requests. And so this from request constructor is what allows us to put these two together. So this says, give me a request of type A, give me a data source that can handle those requests, and that request type has to be a subtype of that request data type we looked at before that tells us it can either fail with an E or succeed with a B. And that's going to give me back a query that will either give me that B or fail with an E. So here we're combining what we want done with how we want it done to build a query that actually knows how to access this data source and return a result for us. And in addition to this, we've got a lot of other constructors on ZQuery. We can construct it from pure values, but one of the really nice things, and we'll get into this a little bit later on as well, is we can build these queries from ZIO effects. So anything we can do with ZIO effects, if we want to use the console to log some things, if we want to write some things to some other database, if we want to time things, if we want to fork things, anything we can do with a ZIO effect, we can lift into a ZQuery here. So it gives us a lot of flexibility to mix and match things and to get this query optimization when we need it, but to still execute arbitrary effects when we need those. So here's an example of what all this would look like for the simple example we looked at the beginning. So we're going to create this user request trait here, which is going to extend that request trait. And in this case, a user request is going to succeed with some value of type A. We're not saying what that is yet. And for simplicity here, we're saying our user requests can't fail. They're always going to return a type A. And then there are going to be two subtypes of this algebraic data type here. So there's either going to be this get all user IDs, which is just a case object, because anytime we want to get all user IDs, we're just getting all of them. And this is going to return a list of integers, that's the user IDs. And then we have this case class, get username by ID, where we're going to take each parameter to that function and make it a value inside this case class. And again, we're going to extend request, and this time we're going to say this is going to return a string. And so then when we go to implement a data source that's able to handle both of these, we're going to create a data source that handles user requests. And so when we implement this run method, we know we're going to get this collection of requests. This chunk type you can think of as just really a list or a vector if you're familiar with Scala's collections, but it's just essentially an efficient linear collection here. So we're going to have this collection of requests, and we're going to be able to look at them all at once. So for example, we could partition them, and we could say, okay, there's one get all user IDs request, or there are 20 get usernames by ID requests, and then we could at once submit that to whatever data source is underlying this. And this data source is encompassing all that logic so that the higher levels of our program, this ultimately, it could be interacting with SQL, it could be interacting with Redis, it could be interacting with something in memory. We don't need to know that at the higher levels of our application. That's handled at this layer for us. And then with that, we just lift those data sources and requests into a query with that Z query from request constructor. And this is just going to give us the versions of those two methods from the very first slide we looked at. That's going to let us do all of this with that optimization of automatically batching all of these requests whenever it's possible to do so. As well, it's actually going to do caching for us as well, so that even if we end up having different parts of our program logic where we're requesting the same thing, we'll only ever get that once from the data source. So I think this is probably a good time to pause for questions for a minute. This is kind of, so far, pretty similar to the functionality you would get from Haxel, and provides a really nice interface for read-only interactions with data sources, where between this idea of batching and the caching, you essentially get to write your query reflecting its data flow and get the optimal degree of parallelism from that without having to explicitly fork things. So let me see if there are any questions here before we go on.
Sure. So our first questions, the two of them came in a little bit earlier. So somebody was double checking, is this an alternative to HTTP4S?
No, I would say it's definitely, it's not an alternative to HTTP4S. It's something that you would really use potentially with HTTP4S, with Caliban, with ZIO Redis, with some other library that's representing an underlying data source, where this Z query, it doesn't know anything about any particular data source. It knows about this structure that queries have and how to optimize them. So this is something that you'd really use in combination with something that knows how to implement a particular data source to provide a more optimized and composable API for the users of that.
Okay. And then somebody was wondering which languages or paradigms inspired the pipelining model being used.
Yes, so let me actually come back a little bit to the pipelining, because so far we actually haven't done any pipeline. We've only been doing batching. But just to reiterate from the very beginning, the inspiration for this was very much this Haxel library in Haskell, as well as that paper, the There Is No Fork paper by Simon Marlowe and his team.
Great. On slide called Creating Data Sources.
Yes.
It seems like get all user IDs could extend user request rather than request. Maybe.
Yes, that is 100%, and I should have done that. So I will go back and change that. Yes, that is exactly right.
Okay, and he says, and similarly for get username build.
By ID. Yep, 100%.
Okay. There already exists some integrations for data sources.
So the most significant one right now is the one for Caliban that we'll talk about. There's work underway for one with Redis as part of the ZIO Redis project. But for folks who are interested in, I think that's one of the definite potential areas that we can build on here, where this is essentially a tool that lets you abstract for your users over some of the details of how to actually execute these requests so that the users can interact in this kind of nice monadic interface where they use operators they're familiar with. They don't have to learn a DSL from your data source, but under the hood, someone has to write the actual implementation of the data source that's going to look at all these requests and execute them in an efficient way. And so far, some of that's done as a part of a couple of these libraries, but I think there's a lot of potential for people who either have certain data sources they've created or are interested in working with a particular data source to build some of this logic in a way that can be shared by other users.
Okay. And since the interpreter data source that implements the method run only knows about a chunk of request of type A, how does it know to perform batching, and how would it do performance tuning?
So it knows it can perform batching because when it gets this chunk of requests, the guarantee here is that all of these requests can be performed in parallel. So it can look at all these requests and it can perform them however it wants. It can say, there's the first and the last one are looking for the same thing, and I can do those as part of the same thing, and it can reorder them however it wants to. So that's how it knows that it can do that. And as far as performance tuning, again, it has that information of here are all the requests I'm getting, at least all the requests that I'm getting right now that can be done in parallel. So it can decide, hey, I got 1,000, that's too many for me. I'm going to do 100, and then I'm going to do the next 100. I'm going to break them up that way. It can do them all. One of the things we'll get to a little bit later is there are also some combinators we provide that lets you do that tuning. So for example, if you say, I only want my data source to deal with 100 requests at a time, I don't want to get overwhelmed by dealing more than that, you can specify a maximum batch size, and we've got some nice combinators that let you do that on the fly. So even after you've created this data source, you can kind of modify that after the fact, and we'll come back to that a little bit later on.
Okay, does the actual batching have to be done by us in the run function? Say like batch queries to the database, and ZQuery provides for batching.
Yeah, so this is kind of where you have to do the logic that's specific to your database or whatever your data source is here. So you've got to say, okay, I'm going to take all these user requests and I'm going to, let's say, fold over them. I'm going to collect all the ones that are get username by ID requests with their IDs, and I'm going to reduce that to, say, a list of IDs, and then I'm going to grab all of those IDs from the database. So yeah, this is where you build in the specific implementation here. This is essentially preserving for you the information to be able to do that, even though the original query wasn't written with that in mind.
Okay. Is there a way to get some instead of all or one? For example, say I have a query that's going to get me 10 users, but let's say I work for Facebook and have billions of users. So 10 queries won't be great, but getting all user IDs might not be a great idea either.
Yeah, so this was definitely a very simple example here of just a illustrative example, but yeah, you could say instead of being case object get all user IDs, this could be final case class get friends of, or get user IDs in range of. Essentially anything here you could think of, if you want to make it instead of just a val that returns one thing, if you want to make that a function that returns users based on some input, you can just model that as a case class like this one is, with whatever you're going to use to select those users, whether it's a limit or whether it's some parameter you're going to filter on, or any other input that you need to get the users that you want.
Great, that's all we have for now, so we can continue and, oh wait.
Awesome.
Does there exist any tooling to preserve ordering on the output? If input data was in custom order and we do parallel requests and want to get a final result in the same order as the input was.
Yeah, so you are going to be guaranteed to get the results in the same order. And that's where the fact that you've got this case class that has an ID comes in, because essentially this is going to be used as a key of the underlying implementation is going to run all these requests, put them in this map, and then associate them back with the original requests that correspond to them. So yes, you don't have to do anything else here, but the framework will handle that for you, and we'll make sure that when you get back those user IDs, they're in order versus in an arbitrary order.
Great. All right, so I think that's all we have for now, and we can come back to more questions later when you're ready.
Awesome. So from there, so we saw, okay, we can put all this together, we get this optimized query, and then we can just use this run function to convert it back into a ZIO effect. So you've got this nice overlay of you can lift ZIO effects into queries, which have this additional structure for query optimization. And when you've got the structure you need and you've put together the queries you want to combine, you can run them back to a ZIO effect that will describe performing that whole query and returning its results. And then you can combine that with further parts of your ZIO program. So it all fits together very nicely. So let's see a little bit about how this works for Caliban, which is the main user of ZIO Query right now. So Caliban is a really great library for doing GraphQL in Scala by a friend of mine, Pierre Cadeau. It does automatic derivation of schemas from data types. So you essentially just write a set of case classes and sealed traits, algebraic data types in Scala that describes your schema, and it'll automatically create a GraphQL endpoint based on that. It'll do parsing and validation of queries, and all the effects are handled on the back end by ZIO. And it's got a really nice integration with zQuery built in, where, again, to model your schema, you would just create case classes here. So like, to go back to kind of a running example, you would do case class queries, and then you'd have a users query that is going to return a list of users. And here you've got a user query that's going to take some arguments about the user and is going to return that user. And if you want to get optimization here, you would just replace ZIO or no effect with zQuery here. And Caliban's automatically going to take all these things and combine them together so you get that maximum degree of parallelism. And so to see an example of this in action, this is an example from this blog post that someone did on optimizing your GraphQL queries. So this is an example of a moderately complex query that is essentially going to look up a user ID, look up what events that user has coming up in the future, and then for each, look up some information about metadata, venues, tags, then which friends are attending, and then information about those friends. And so if you execute this in a naive way, this will take 47 different requests. If you do everything in parallel, you can potentially do in parallel, this will go down to just 8 requests. And this is exactly what you get going from the naive implementation in Caliban to the optimized implementation. So between a really simple change of essentially going from a ZIO effect here to a zQuery effect here, which really basically has all the same combinators that you already use on ZIO in terms of zipping and mapping and flat mapping and folding and everything you're familiar with if you do anything with ZIO, just replacing that, again, takes you from this to this. So it's a really nice integration there on top of what's already a really nice library if you're doing anything with GraphQL. So far we've been talking about batching. So let's talk about pipelining. And to motivate this, you can think about, so far we've really been talking about 2 models of computation. So one of them is this sequential and dependent computations. So this, if you're kind of into category theory, you think of this as like monadic computations. And then the second is this parallel and independent computations, which you could kind of think of as applicative computations. And so if you go back to like Haxel or that original paper, it was really about kind of distinguishing these two computations and having one data type that let you have sequential computations, but let you have these parallel computations whenever you could have them. And so sequential, if we go back to like our original example, sequential is what happens between the lines of this for comprehension. If we said we need to get the user IDs, and then after we have the user IDs, we need to get the user names. So we need to do one thing before we can do the other thing. The actual flat map itself gets hidden a little bit here in the for comprehension, but this is ultimately desugared to a flat map call. And when we have something like this, we can't really do any optimizations here because we don't even know what this second query is going to be until we've completed the first query. I mean, here we can kind of just look at it ourselves and eyeball it and say, okay, we're going to get user names. But as far as the compiler is concerned, this is just an arbitrary function that's going to take some A and give us back a new query. So it could be, well, if this says East, I'm going to query the East Coast data center. And if it says West, I'm going to query the West Coast data center. So we don't even know what query we're supposed to be doing. We can't really do any optimization here beyond just do this. And then once we've done this, try to do our best with this. And in this case, implement it in parallel. And then we saw we had this set of parallel and independent computations. So that was like this for each par, where we've got a bunch of user IDs and independently for each one, and we're saying we can do it in parallel, we want to get the user names. And so at least in ZIO and Scala, the kind of fundamental operator that describes this is this zip with par operator. And so here we know both of them in advance. We know we can perform them parallel. So we just batch them. That's kind of what we saw in the first part of that talk. Great. But if we think about this, we've kind of talked about two different things. We've talked about this idea of sequential versus parallel, and then dependent versus independent. So you can kind of think of, we've got like a 2x2 grid here. We've explored two of the possibilities. One of the possibilities doesn't really make logical sense of saying we're going to have parallel and dependent computations, because then the dependency implies that they can't be parallel. But there's actually another possibility that we haven't really considered, and that's this idea of sequential and independent computations. So this is something that actually came up in some of the work on ZIO Redis, and I think at first it was a question from Dion, who's I think is going to be talking to this group later this year about STM. But the idea is, consider a query like this. So we're going to increment some key in a cache. Then we're going to do this ping operation, which let's assume that this is going to take a snapshot of whatever the source of this data, whatever the data in this data source is, whatever the state of it is, and return that back to us. And then we're going to decrement some other key. So this actually doesn't really fit in either of the models we've talked about so far. It's not something we can do in parallel because the ordering clearly matters here. If we do this ping first, we're going to get a state that doesn't have this key incremented. If we do it last, we're going to get a state that has this key decremented. And both of those are different than what this is guaranteeing us, which is that we should get a state that has this incremented, but not this decremented yet. So we definitely can't batch these things and implement them in parallel. And so like if you look at other, like that Haxel library or other libraries that do this, this would normally just get translated into flat map and then another flat map here. So this would just be three different things we did. But if we think about it, we're actually throwing information away when we're doing that, because we know statically what each of these three things are. So we should be able to do some optimization here. And this is what we call pipelining. So ideally, you would say we should be able to transmit all of this to the data source at once, since we know the structure of it up front, and tell the data source, hey, when you execute this, you need to make sure to execute it in a way that honors this ordering guarantee. So what does that look like? Well, we're basically going to build on the same approach that we talked about for the batching. So we're just going to need to capture more information in the structure of our query. Where previously we captured the overall information of the query itself, its parallel and sequential structure. But when we got to those blocked requests, we essentially just treated them as one collection. So we're going to need to keep more structure there that tells us when we're blocked on a set of multiple requests, are those things we can execute in parallel or things we can execute sequentially. Then we're going to have to use that information to determine when we can safely combine multiple sequential steps like we looked at. And then finally, we're going to have to pass this to the data source in a way that the data source can take advantage of this information, optimize it. So for the first step, we're going to expand that block requests type to, instead of just being a set, to essentially being a free semi-ring. So it's going to have this single case. It's kind of like what we looked at before, where we've got some data source and some request to data source. But we also have this both case, that says these are two things that can be executed in parallel. And this then case that says we need to execute this, and then we need to execute this. And so just these constructors let us describe in a lossless way the structure of parallel and sequential computations. Then the next thing we need to do is we need to use that information to determine when it's safe to pipeline two of these requests that need to be executed sequentially. And the rule we can use there is we can say we can pipeline two of these requests if no effect is guaranteed that it's going to be performed before one and after the other, right? So if no one else is guaranteed an ordering with respect to these two requests, then we can execute them at once and without changing the meaning of our program. And so as a simple example of this, if we have a situation like this one where we're saying, want to do request one and we want to map its result with some function f and then do request two, this we can pipeline because f is a pure function here. So if we do one and two, and then we take whatever the result of one was and we transform it with f, the fact that we maybe did one and two together and we did two before we actually did f isn't observable. So this we can pipeline. But on the other hand, if we have something like this, where we're flat mapping that first request with some arbitrary other effect here we can't pipeline these two because this effect could be printing the result of this first request, or it could be logging something. It could be doing something. It's guaranteed that this is going to be done before this. So we'd potentially be changing the meaning of our program if we pipeline these two together. We can't do that. And then finally, we need to augment our data sources with the ability to support this. So now that run function becomes this run all function that now takes two chunks of requests. So this first outer collection of requests is batches of requests that need to be executed sequentially. So the data source can look ahead and see all of them, but it's being told you need to execute these in a way that honors this ordering. And then the data source can introspect on that and it can determine what optimizations it can safely do. So for example, it might be I'm incrementing one key in the first step here, but that key is not being dealt with in any later steps. So then I may be able to parallelize some things because they're interacting with different keys in the database, even though here I said these were going to be executed sequentially. So you have this ability to do look ahead, but you're being told as the implementer of this what ordering guarantees need to honor. And then this inner chunk represents requests that can be executed in parallel, the batches that we looked at before. And we've also got a type alias for this that only does the batching. So essentially, if you say, hey, this pipelining stuff is great, but I don't need that right now. I just want the batching. I don't want to deal with having these two different things. That's totally fine. We've got a way for you to do that that's very easy. So that's pipelining. So batching and pipelining, these are kind of these two modes of computation that we support here. Maybe before we go on, any other questions at this point?
So I don't have any questions, but somebody just raised their hand. So if they can send it to me, I'm happy to ask it. But yeah.
Okay, well, let me, I don't think we have too much more to go here. So let me keep going then, and then we hit other things at the end.
Sounds good.
So what else do you get here? So you get caching. So zQuery gives you the ability to automatically cache and deduplicate requests. So we hit on this a little bit before when we were talking about the batching, but this can be really useful, especially for those read-only queries, because it lets you sometimes write your queries in a very natural style where, maybe in the past you said, well, look, I need the same information 2 or 3 different places. And maybe you say, well, I don't want to be doing the same work twice. I don't want to be inefficient. So I'm going to move that code somewhere else so that it's earlier, so that I can use that in multiple places. This says, don't worry about that. Write the query the way you want to write the query. We're going to make sure we only ever make that request to the data source once. So between that and the automatic parallelism, it can be really nice there. And the other nice aspect of that is it can also create a consistent view of the data in the face of potential changes. So you can imagine if maybe your query has multiple steps, multiple times you need to go back and make requests here. If this is some type of live data that other people are writing to and potentially changing, you could have this situation where you're kind of getting inconsistent results when you do different requests here. Whereas by caching them, zQuery can give you kind of a consistent view of this, at least as of a certain snapshot in time. The other nice thing about the caching is it's totally optional, particularly as you do more write queries. It can actually be something you don't want, because you don't want the write to be cached. You want to kind of make sure that that happens when you tell it to happen. So there's an easy construct that lets you determine whether that should be cached or not. Another nice thing is combinators on data sources. So these data sources, so far we've just talked about creating them and implementing these like run or run all functions, but they're values themselves that can be composed in some interesting ways. So for example, we've got a race combinator that says you can take 2 data sources that both handle the same type of requests, and you can put them together into one data source that will take whatever request you send it to both of those original data sources, return the results from whichever one completes first, and interrupts the other data source. So if you had like your East Coast and your West Coast data centers that have the same information, you could create one data source that describes this process of try both of them and return the one that gets back to me first, and has all the same ZIO logic that you've seen in ZIO itself and ZStreams and managed to do safe interruption, all of that. Another useful one is this batch end combinator, which goes a little bit to one of the questions earlier of you could say, okay, this is great to have the batching, but I don't want my data source to be getting 100,000 requests. That's too many for it to handle. I only want it to deal with 100 or 1,000 or however many at a time. So we've got this really easy combinator to do that. And then another nice thing that builds on that is this idea of data source aspects. And so a data source aspect, if you're familiar with ZIO test, it's kind of like a test aspect. It's something that has the ability to transform data sources without changing the type of requests they can accept. And so it's a really nice tool to be able to either collect metrics, add logging, or modify some aspect of how queries are executed. So like that maximum batch size, there's a data source aspect for that where you don't even have to apply the maximum batch size at the time you create the data source. You could only apply that later on when you write a query, or you could even only apply it to part of a query. Or we have another one that lets you perform an effect before and after each time a query is executed. So that also gives you some nice composability here. And then finally, we hit on this a little bit before, but just to come back to it, the fact that you can do effects and lift them into queries can be really nice for things like, here we've got a simple example of timing a query, very easy to do, basically the same operators you have for ZIO of you can just time how long a query takes. And here we're bringing that same like clock functionality, very familiar to what you'd have from using ZIO. And you have essentially all the combinators you're familiar with to access the environment, provide the environment, transform and recover from error types. So if you're used to working with ZIO or really used to working with another functional effects system, it's very intuitive to do all the things you're used to doing with queries that you're used to doing with other effects. So to summarize, ZIO Query lets you add efficient pipelining, batching, and caching to any data source. It's great if you want to optimize requests without creating a domain-specific language. So you could imagine for either a simple example or more complex ones, you could create your own essentially DSL. You could imagine, there's a whole project ZIO SQL to let you write SQL queries in a type-safe way in Scala. And if all you're doing for a set of your program is SQL queries and you want to work on that level and you want to optimize on that level, that's fantastic. But a lot of times we want to do some of these requests to data sources as part of what we're doing. We want to be able to get most of those optimizations without having to drop down into that domain-specific language in kind of the same style that we use for the rest of our code. And ZIO Query is really good for that and letting you use the combinators you already know in the approaches, but getting this additional degree of optimization. So finally, before I turn over questions, want to say some thank yous here. So first to Pierre, he's been a fantastic collaborator on ZIO, done a really fantastic job of, great idea to begin with Caliban, and then it's incredible to see kind of what he's done with it and the community he's been building around it. In addition to all that, I think he maybe seems even more cool because he's got this cool Ghost Dog PR name he uses, and we've got the little like duck icon here. So he kind of seems like the international man of mystery. But thank you very much for kind of taking a chance on a new solution here for this. Thank you, John, for really creating a tremendous amount of opportunities around ZIO and being a mentor to me personally and multiple iterations on various aspects of this. Thank you to all the Caliban users and contributors who've used this and given feedback as we've grown here. And it's been really great to see the community that's grown up around that. Thanks to Courtney and everyone else involved in organizing this conference for putting this together and the opportunity to speak here. And finally, thank you to all of you for taking the time to listen to me talk for an hour. Hopefully this was helpful and enlightening. But with that, I'll take any questions.
Thank you, Adam. We're certainly happy to have this talk and very much enjoyed it today. So thank you very much. We do have some questions, so we can
Awesome.
go into that and have some more fun with that. So question 1, can you speak about caching for selects where we have hits and misses and evictions due to memory limit for the cache with respect to the data that we want to exploit?
Yeah, so the default implementation of the cache is in memory cache. So you would just be hitting on the ones that you get something for, and they would be kept in memory for the life of this query execution. The cache implementation is extensible. So if you're interested, you can create your own cache that implements this interface that has eviction logic. And if so, then when something gets evicted, then the next time that comes around, that would get re-executed. I don't know if someone has done that yet. So that would definitely be an interesting thing to look at and potentially an interesting PR of we could potentially have some different kind of default implementations that users could select from.
Okay, so is this project conceptually different from Fetch?
So they're both targeting a similar problem, and they're both inspired by that same Haxel library in Scala, or the Haxel library in Haskell, excuse me. So there are some definite similarities there. I think key differences are one, the support for pipelining. That's a whole model of computation that Fetch doesn't have any concept of at all. So it's either completely parallel and can be batched, or it's completely separate. We're going to do this query, that query, the other query. There's no ability to do this type of pipelining. Another difference is in type safety. So these requests and the way we use the completed request map to allow having data sources that support more than one request, but making sure that you can only fulfill a request with a response that's of the appropriate type is something that you don't get in Fetch. And finally, what you get is all the power of being built on top of ZIO and not having that kind of tagless final style. So you get an environment type, you get typed errors, you get to take advantage of kind of the safe interruptibility of all of that. And you get much better type inference because you don't have kind of that like F type parameter everywhere. So those are some of the key differences versus Fetch.
Awesome, thanks. So can one use database or DB as a source like PostgreSQL?
Yeah, definitely. I mean, the idea of this is really to be kind of agnostic of the actual underlying data source, but you 100% can use a database as the underlying kind of implementation of that data source here. One of the nice things is you've also got that environment type to help you out. So we didn't really come up here, but if you go back to data sources here, they're parameterized on an environment. So you could imagine that this run function is actually implemented in terms of some database call. And then you even have the power to use that environment type to express that you depend on Postgres or you depend on some type of SQL database, and then even defer what that implementation is to a higher level of your application. And another thing that you get here is you potentially get the ability to abstract over multiple data sources. So far in this talk, we really kind of focus just on like how this works and how we optimize a single data source. But a lot of times what you actually have in your application is you may have different data sources. You have something in Redis, you have something in Postgres, you have something somewhere else. And one of the really nice things about ZIO Query here is you can create a data source for each of them, and each data source knows how to run and knows how to optimize requests to that data source. But when you then ultimately go to write your code, you can get something from this data source, something from that data source, something from some other data source, and put them together all in the same type of straightforward logic here, without kind of the person who's doing this type of more business logic needing to be concerned with maybe get all user IDs is actually requesting from some Redis data source, and this get username by ID, maybe this is requesting from a Postgres data source. That's handled at this level. It doesn't need to be handled at the level of writing this kind of logic.
Okay, so one more, unless somebody else is typing in. I'm curious to see what ZIO Query could do for special or temporal queries. Can you talk about that?
I'm curious to see what we could do as well. That's definitely an interesting one there, that you can see some logic being built into data sources to essentially maintain part of that information of you have overlapping queries for say different periods of time, kind of going back and looking at that and saying like, hey, you already asked me for midnight to 1 p.m. and now you're asking me for noon to 2 p.m. So some of that's already in there and I can grab that. I think that's possible with what we have here. I think there's definitely some that goes back a little bit to the logic of that data source implementation to say, how are you actually going to use that? But yeah, I think that's a really interesting idea.
What about data updating?
Yeah, so that's really where this pipelining comes in, and your ability to decide whether or not you want to do caching here, because it's really updating and essentially writing data that this type of ordering becomes important. Because if all you're doing is reading, then other than I need some input to my next query, everything can happen with the maximum degree of parallelism. It's really this type of case where you're starting to do some type of updating where the ordering becomes important because maybe one update depends on another. So that's where the pipeline really comes in, that you can express what those ordering guarantees are in a very straightforward style with just, I mean, I guess this is a little bit of a Haskell or now a ZIO, probably a Scala functional programmism, but this operator says, do this effect and then do that effect. And you've got those same operators you can use with zQuery here that will honor that ordering guarantee, but still optimize to the extent we can. So that's really where the updating comes in.
Somebody else wants to know if it is useful to combine ZIO SQL and ZIO Query, or will ZIO SQL as a dedicated SQL DSL already do everything ZIO Query does?
So I think it's going to be a little bit of a trade-off for users in terms of power versus usability. So ZIO SQL is going to kind of provide you like the full power of writing SQL queries. It's going to be the most efficient thing. You're going to have to do some effort to learn. One, you're going to have to obviously know SQL yourself, and two, you're kind of going to have to know the ZIO SQL encoding of that. So if that's like the problem you're trying to solve, that's 100% going to be the best tool for you. What this may be more useful for is if you've got a certain subset of SQL queries that you want to do, and you want to expose a couple of them as part of your broader application and do it in a way where it's very easy for the user to include those with maybe queries from other data sources, maybe other effects. This is really just a part of what you're doing. Then you could see, I think, ZIO Query potentially being a layer on top of that that provides this more convenient API to the user.
Awesome. Thank you so much, Adam, for this talk and for answering all of these questions. And it's been a great session, I think. So thank you very much for being here today. And we're glad you could come.
Thank you so much, everyone, for your time.